So let me share today's slides. Can you see the slide in full screen mode? Can someone respond, please? Can you see the slide in full screen mode?
Yes, sir.
Okay, thank you. So in today's lecture, we are going to have a discussion on the basics of instruction pipeline. For that, I'm going to introduce you to the RISC processors and its instruction pipeline design. So introduction to RISC instruction pipeline. In the last day, we have been trying to see how can you evaluate the performance of one computer system with respect to other. And we have learned some of the quantitative parameters or metrics that we generally use, out of which one is the response time, and the another parameter was throughput, then speed up, many other parameters we saw. We are going to focus on one thing very specific that computer architects have worked in the last 3 or 4 decades. How can you improve the performance of a processor? And one such important step was about having an instruction pipeline. Here the focus is to improve the throughput. Can you increase the number of instructions that are executed in a given time? You know that every instruction will take some amount of time to execute. Now, let us imagine that one instruction is going to take 5 cycles. And if you have 100 instructions, then our normal expectation is 100 instruction will take 100 into 5. That is 500 clock cycles. Now, through the concept of instruction pipeline, we are trying to improvise on it, and let us see how it is being done. So I'm going to introduce you to a RISC microprocessor, which is known as MIPS. It is the abbreviation of microprocessor without interlocked pipeline stages. So this microprocessor is a general purpose microprocessor which has 32 registers, and each of these registers are of 32-bit in capacity. Means I can store a 32-bit value in each of these registers, and the registers are named as R0, R1, R2, etc. up to R31. The next peculiarity of this microprocessor is all the instructions are of uniform length, and it operates on RISC architecture, and that is a load store architecture. I'll come back to all these points. Now, you might have learned about the initial days of this course when Professor Deka was taking the class about what is the role of a program counter, what is memory address register, like that. So you know that in order to carry out execution, first we have to fetch an instruction and decode the instruction, and then you execute it. And sometimes you may have to store the result back in memory or registers. In the meantime, your program counter is getting updated such that your program counter will reflect what is the address of the next instruction. Now, looking through that, if you go, how do or have you ever thought of what is the logic behind incrementing of the program counter? So, program counter is currently updated on, let's say, 3000 is the point where program counter is currently pointing to. That means it is the address of the next instruction to be fetched. That means the next instruction is kept in physical memory address 3000. Now from
Excuse
3000
me,
it moves.
sir.
Yes.
Sir, the slides are not visible in full screen mode. That's the slides are not running in presentation in case you have started the presentation.
So you cannot see the slides now?
I can see the slides, but that PowerPoint mode is just visible. The full screen mode for the presentation is not visible.
Okay. Can you see the slides now?
It's loading, sir. I will let you know as soon as it loads.
So I have stopped the sharing now. I was just seeing. Can you see the slides now?
Yes, sir. Now it is there in the full screen mode.
Okay, the title shows the introduction to MIPS, right?
Yes, sir.
Okay, fine. So I am talking about a microprocessor. With the help of this microprocessor or with the example of this microprocessor as a case study, we will try to understand what is going to be an instruction pipeline. Now, we are already discussing about the concept, what is the role of a program counter. Program counter contains the address of the next instruction to be fetched and executed. So imagine a case that your program counter value is 3000. That means the next instruction is to be fetched from memory address 3000. Now, once that fetching is over, your program counter is updated to the beginning of the next instruction. So where is the next instruction kept? Because we know that all instructions are kept sequentially, one after another in the memory. So the first instruction is going to take, let's say, 3 bytes. Then my next instruction should be loaded at 3003 because 3000, 3001 and 3002, they are going to be part of the first instruction. So the second instruction starting at 3003, let us say it is a long instruction which is spanning across, let's say, 8 bytes. Then the new instruction will be kept at 3011. So generally, we have a broader division of architectures, microprocessor architectures, based upon what is the complexity level of instruction. And that classification is known as RISC and CISC. RISC stands for Reduced Instruction Set Computer, and CISC stands for Complex Instruction Set Computer. Generally, RISC architectures, all instructions have uniform length. So here we have uniform length instruction. That means every instruction is of 4 byte. So all instructions are going to start at multiples of 4. Let's say 3000, 3004, 3008, 3012, like that. So always program counter can be separately updated. I need not look into what is the length of the current instruction. PC is always is equal to PC plus 4 because 4 byte is what the space consumed by one instruction. So that is one of the advantage which will reduce the complexity of a RISC processor. So at the time of the designing of instruction, I hope you have learned about instruction encoding and all. When you design a RISC instruction set, we have to incorporate all the instructions such that they all are of the uniform length. It's a bit challenging task. Sometimes for certain instructions which are mentioned in the implied addressing mode, I may not have the requirement to use all the 32 bits. Sometimes I may require all 32 bits, but for some instructions, there is no meaning to have a 32-bit instruction there. But as a worst case, in order to make things uniform, we may have to add extra zeros to those instructions such that all instructions are of uniform length. If the instructions are not uniform length, then the challenge is every time my program counter has to be added with a different value. Sometimes PC is equal to PC plus 2, sometimes PC equal to PC plus 4, plus 8, because I can have variable size instruction. Generally, your CISC computers, complex instruction set computers, they go for such a kind of a policy where some instructions are long instructions which will take multiple bytes. Some instructions are short which will take only very few bytes. And accordingly, after fetching each instruction, I need to have a mechanism by which I understand the length of the instruction and accordingly PC is updated. Generally, for RISC architectures, we follow uniform length instructions. So what we are trying to learn here is I'm talking about a RISC microprocessor whose name is MIPS, which stands for microprocessor without interlocked pipeline stages, where it has 32 integer registers. Each of these registers can store an integer value in 2's complement form. All instructions are of uniform length. It's basically 4 bytes. And then this is following a load store architecture. What you see on the right side diagram, that is a load store architecture. On the top side, we have processor. On the bottom side, we have memory. Both are independent component, and you have your buses, the address bus and data bus that connects processor from memory. When I talk about load store architecture, which you can understand from this diagram, you can see that the ALU, which performs the task or operations, its input is always from the register. What you see the sequential row there, they are basically your register. So this is basically your register set. So the input to the ALU, both the inputs are all taken from registers and the output is also stored in a register. That means any ALU operation both the source operands has to be registers and the destination operand is also a register. Like add R1, R2, R3. Let's say R1 is going to be the destination register. R2 and R3 are going to be the source register. So if at all you wanted to perform an operation, you should have separate instruction to transfer contents in the memory to some appropriate registers. And at the end, if you wanted to get a result back in memory, I need to use another instruction which will copy from processor register into memory. Essentially, ALU instructions cannot have a memory operand. That is what is known as load store architecture. What yet another description of this is, there are only two instructions which will touch memory. One is a load instruction, whose meaning is transferring something from memory to processor. That is known as a load instruction. And the other one is known as a store instruction. That is something that will transfer the contents from registers back to memory. So loading is a read operation, memory to processor, and storing is a write operation. It's from processor to memory. So using this load and store instruction, I could transfer data between memory and registers, and any operation that you perform, it has to be done only with the registers. Because when you know that when you go to memory, like Professor Deka earlier mentioned, we have different hierarchy levels of memory. We have cache memory, we have main memory, we have disk, like that. So there is no guarantee that whenever we are going to try or to access something from memory, it may or may not be present in cache, because cache is very small. Only a subset of main memory components can be kept in cache. So there's no guarantee in that. So load and store operations may not give you result in a definite amount of time. If it is a cache memory hit, it will get in, say, 10 nanosecond time. If it is a cache memory miss, there are different levels of cache. So if you get from L2 cache, then it may take a little bit more. If you are not going to get anything from cache, then you may have to go to memory. So in load store architecture, only load and store instruction have a variable time for execution, whereas all other instructions are happening internal to processor, so they will complete in a definite time. When you know that add R1, R2, R3, all the operands are present in registers. Destination operand is also a register. So reading from register, constant time. Performing an operation in ALU, another constant time. Writing the result back to one of the register, yet again constant time. So any ALU operation will get completed in constant time. So this is the summary of a MIPS process. Basically for MIPS, there are three types of instructions. You might have already learned about instruction encoding. Given certain number of bits, how do you define the meaning of each and every bit, or how the decode unit will be able to understand what is the operation that is being specified. So let us come to the first instruction type. This is called R type. So I already mentioned that each instruction is 32-bit. Now, out of this 32-bit, in R type instruction, we have a 6-bit opcode. All R type instruction, there are three register names, RS, RT, and RD. Each of them is 5-bit. Using 5-bit, I can have 32 combinations. I have already mentioned that we have 32 registers. So if you wanted to say add R1, R2, R3, you write R1 here, value 1 here in 5-bit, 0, 0, 0, 0, 1. This will be another 5-bit for first operand, another 5-bit for the second operand. And this will basically tell you what are the functions and what is the shift amount. So this 5-bit is used only for a shifting operation. So traditionally, R-type instruction means you have a 6-bit opcode and the name of 3 registers would be mentioned. And there is a function code also within add type or within subtraction type. What are the various functionality that I can do? Coming into, so we should not worry too much about what is the meaning of each and everything. This is just to give an overview. The second category is known as immediate instruction, where I will be specifying, along with opcode, I will be specifying 2 register names also as part of this, RS and RT. One is the source register and the other one is the operand register. And then there is a 16-bit immediate value that I am also going to tell. That means it can be a load, R1, R2, and then a 16-bit number. The third category is known as a jump instruction, which has a 6-bit opcode, and then there is a target address, which is for 26-bit. So if at all I wanted to jump from one location to another, this will tell you the relative distance from the current program counter value to the new target value. This is always so relative, PC plus whatever value you have put in the target address, which will essentially realize a go-to operation or a jump operation. So this is the three types of instructions in MIPS. Now, before introducing the pipeline, let me draw your attention to a laundry example. Think of a case that there is a housing colony where there is 4 families and there is a common laundry service there. So let us say family A, they are going to dump their clothes in the laundryman, and there are basically 3 operations as far as laundry is concerned. Let's say it takes 30 minutes of time to wash the clothes, 40 minutes of time to rinse and dry the clothes, and 20 minutes of time in order to iron the clothes or fold the clothes and iron it. So totally it is 30 plus 40 plus 20. That makes total of 90 minutes of work is there. Imagine these are 3 equipments. One person is taking care of, you put inside the washing. Once washing is over, you put it inside the rinsing and the heating unit, the spinning unit. Then you take it out and the person will iron the clothes and keep it ready. So it has been done by 3 separate individuals, part of a laundry. So it takes 90 minutes to complete the washing of one family. Then let us say there is one more family B, which will start. So which will take next 30 minutes for washing, 40 minutes for drying, and then 20 minutes for ironing. And then we have the third family. So each family can start the operation only after the previous one is over. So this is known as a sequential laundry. So if you take 90 minutes is there, 90 into 4, and so that much time you are going to take in this case. And you see that is going to take 6 hours of time. So 90 into 4, that is 360 hours. So 360 minutes, that's basically you have 6 hours of time in order to complete 4 loads. Now, can you optimize this? That's what the question is. In the same laundry example, we know that we can go for a pipelined laundry. So what you do is your work will start as soon as the machine is free. So you have basically 3 subcomponents: a washing component, a drying component, and a folding component. So once you put things into this, you can start washing the next set of clothes. So I should not wait for the entire process of A is over, because these are 3 independent units. The moment washing unit is free, I can dump the clothes of B into that. So it takes 40 minutes there. So out of that, even though it's 30, 40, and 20, I can initiate a new operation only at intervals of 40, because out of the 3 operations, 30 minutes for washing, 40 minutes for drying, and 20 minutes for folding. 40 is the larger one. So operations are moved from one unit to another only at intervals of 40 minutes. So the first one will take 30. Then at the end of 40 minutes, washing of B starts. End of next 40 minutes, washing of C starts. End of next 40 minutes, washing of D stands. So when you look at this way, that is this vertical column, the drying process of family A is happening at the same time. Sorry, the folding process of family A is happening. At the same time, the washing process of family B is happening, and the drying process of the next family is happening. So like that, you can look at vertically, the person who is in charge of folding, he is busy. Person who is in charge of drying, he is also busy. And the person who is in charge of washing, all the 3 are busy, but they are busy with 3 different set of workloads. So when you go for a pipelined laundry, it takes only 3.5 hours to complete all the 4 loads. And now if you look at the number of families work that is completed, the throughput increases. Actually, if you look each individual one, there is a slight increase, because now it becomes 40 plus 40 plus 40. It becomes 120 minutes. It's slightly more than 90 because of the unequal length of each unit, but the throughput is going to increase. So individually, if you take one family, they may not get any saving. Rather, they are getting penalized more because of the unequal delay. But if you look overall, the number of tasks that is completed per unit time has significantly improved. So from 6 hours, now we are coming to 3.5 hours. This is the same concept what we are going to apply in circuits also. What are the pipeline characteristics? Pipeline doesn't reduce the latency of a single task, but it improves the throughput of the entire workload. And the pipeline rate is limited by the slowest pipeline stage. So here we know that 40 unit of time was the slowest in the pipeline, and the potential speed up that you are going to get is equal to the number of pipeline stages. And the unbalanced length, here we have 30, 40, and 20. The unbalanced length of the pipeline stages will reduce the speed up. And the time to fill the pipeline and time to drain the pipeline also will reduce the speed up. So let us come to pipelining in circuits. So what you do, let us say if you have one circuit which is capable of performing your fetching operation, decoding, reading the operand, performing ALU. Let's say it's a one macro big circuit, let's say a sequential circuit. You give the instruction at the end, you are getting the result. You don't know what is happening inside. It may take multiple clock cycles to complete the operation. Now, can I subdivide this circuit? So that is called an unpipelined circuit. Given a task, it takes multiple cycles to complete the operation. Now, coming to pipelining, what you basically do is you try to divide this macro unit into smaller subcomponents. We know that in the instruction execution, there are subtasks such as instruction fetch, instruction decode, reading of the operand, storing the address, loading from memory, writing into registers. All these I am going to divide into smaller independent tasks. So if you try to rephrase the sentence, pipelining partition the system into multiple independent stages with added buffers between these stages. Just a quick question. Can you see the slide now? Is the slide in the full screen mode?
Yes, sir.
Okay. So pipelining can increase the throughput of a system. So look at the diagram. Initially, you just consider, let's say there is a combinational logic where there are n gate delay. That means once you apply a signal, it passes through n gates one after the another. So the bandwidth you are going to get is 1 by n. Now what you divide, you are going to divide this combinational logic into two subcomponents, equal subcomponents, where each one is having n by 2 gate delays. In between, I'm going to add some latch. So what is the beauty here is, as and when the operations are completed in the first half, you store the result of that in this latch. In the next time epoch, whatever is available in the middle latch, that goes to the second n by 2 gate, whereas a new set of value can be loaded to the first n by 2. So now, if you look at the left side portion, that is already having some kind of a signal that is flowing through that. Right side is having some other signal. They are part of two different instructions. I can further divide this n by 2 to n by 4, n by 6 like that. That's what you can see here. There is a division of n by 3. So the beauty is, at 1/3 of the time, I can initiate a new operation. So the bandwidth that I'm going to gain is now 3 by n. So even though as far as a single instruction is concerned, previously it has to go through this. Now it has to go through the latch, go to the first n by 2 delay, get itself stored in latch, again read from latch and go to. So some additional delay will happen because of the intermediate latches. And these latches make sure that you are going to start everything together. So at the beginning of a clock cycle, the instructions or partially processed instructions are available in the latch. Now as the clock ticks, the extreme rightmost n by 3 gate delay unit that is going to read from this latch, perform the operation and generate the output. At the same time, the middle component, the middle n by 3 gate also read from the latch, performs the operation and write the result to the rightmost latch. Whereas the first one will read from the leftmost latch, perform the operation and write the result into the middle latch. So by the time you complete a clock cycle, they have completed the operations. Each of them have completed the operation and they will write the result into these latches. This is an ideal scenario where you assume that there could be, you are all going to divide into equal time units. Let us say you can divide 30 nanosecond, 30 nanosecond. So let all the three are going to take 30 nanoseconds each. What if one was 30, the left and the right were 30 and the middle one was 40? So even though the left side unit and the extreme right side unit will complete their operation at the end of 30 nanosecond, they will write the result into the appropriate latch. The middle one will complete only at the end of 40. So I can trigger the clock only at intervals of 40. So triggering a clock or initiation of the next instruction will happen based upon which of the one is having more latency and delay. Okay, so for a RISC instruction data path, we can divide it into 5 major sub operations consisting of instruction fetch, the decoding the instruction and reading the operands, that reading from the registers, that is called the register fetch. Then I perform an execute operation, or basically address calculation, and then we have the memory access operation and then a write back operation. I will come to each one of this. So it's basically the execution portion where the ALU is being connected. Imagine this is a black box. So where you give the address and this address contains the instruction. So you carry out all the operation and the result is there. This is an unpipelined design. So wherever you see this dotted arrow, based on this dotted arrow, I can divide this entire circuit into 5 independent but connected sub-circuits. So the first subcomponent, we call it as instruction fetch. Second subcomponent will take care of instruction decode and register fetch. Third is called execute or address calculation. Fourth is accessing memory. And the fifth is going to be write back. So the first one, you are going to read something from memory. And the fourth one is also, if at all you wanted to read any data operation from memory. So you know that we are going to work with the RISC architecture. It is also known as load store architecture. So for RISC load store architecture, you know there are only 2 instructions which will touch memory. The load operation, where the contents are transferred from memory to the register, and the store operation, where the contents are transferred from the register back to memory. So these 2 operations happen during the memory access time. So these are used only for a load or store instruction. And the write back stage is used whenever the result of an operation is to be written into a processor register, then that happens in the write back stage. So this is the general diagram. I will come to each of these components when I discuss them in detail. So this is an unpipelined design. So how do you pipeline it? Wherever you see this dotted line, I am going to add a latch or a pipeline register in between, which acts as an interface. So this is the way how it looks like. It's like a pipelined RISC data path. So what is data path? The path through which your operand is actually moving. So what you see here in memory, so instruction fetch means give an address. So whatever is the program counter value, based on program counter value, it goes through the memory. From memory, it reads the contents and it plays in a register known as IFID. If you look at these green color registers, you can know that each of these registers, which is also known as a pipeline latch. Latch means it to hold the data for a definite amount of time, prefixed time. Let's say it's 1 clock cycle. At the end of the 1 clock cycle, data is being taken by the next unit. So this is not for long-term storage. Latching means you store the data only for a predefined amount of time. And you can see each of these components, what happens. So pipeline the RISC data path. So first section will perform instruction fetch and decoding happens in second. Third, you perform the execution operation as far as an ALU instruction is concerned, or you perform the address calculation if it is a load or a store instruction. So ALU is used for calculation of address. We'll discuss about it in the subsequent slides. Now for non-load, non-store instruction, the fourth stage is meaningless. There is nothing that has been done in the fourth stage. I simply bypass it. And the fifth stage is all about writing the result back into a register. Fourth stage is accessing memory. If it is a load or a store instruction, your address calculation happens in the third stage. And based upon that, you go to the memory. If it is a load operation, you go to the memory and then get the data from memory. And that result is going to be kept in mem write back register. If it's a store operation, the ALU will tell you where to write. And based upon that, you write the content also, which is available here, into the memory. So this is the way how things are going to work here. Okay, so now let us look into, so what this RISC MIPS instruction pipeline tells is, each instruction can take at most 5 clock cycles. Every instruction will take. So the instructions are also designed in such a way that every instruction has to go through all these 5. So if I start at n plus 4, it gets over. N plus 1, n plus 2, n plus 3, and n plus 4, this is over. Someone will start at n plus 1, get over in n plus 5. So every instruction is going to take 5 clock cycles. Let us now see what happens in each of the case. So first stage is known as instruction fetch. So what happens, based upon the program counter value, you fetch the instruction from memory. So this is the program counter value which is available in the address. It pass through the address decoder and reaches the memory. And from memory, what you bring an instruction. And how big is an instruction? It is 32 bits. That means 4 bytes are transferred from memory. So you have a 32-bit wide data bus that is connected from memory to processor. So these contents will reach the IFID register. So why the name IFID? Because it is interfacing between IF stage on the left side and ID stage on the right side. That's why the name is known as IFID. And then you have to increment PC. So with what I have to add, what does PC hold? It holds the address of the next instruction to be fetched. And how will I know the address of the next instruction? Here comes the beauty of RISC. Every instruction is only 4 bytes. So every time PC is equal to PC plus 4. So I have a separate dedicated adder in this stage where the program counter value will come as one input of the adder. A fixed value 4 is coming as a second input to the adder, and PC plus 4 is being done. It is from this PC plus 4 I will bring the next instruction. So since all the instructions are of uniform length, I can perform this PC plus 4. Had it not been a RISC architecture, had it not been non-uniform, suppose if instructions are of non-uniform length, then PC should be sometimes incremented with 4, sometimes with 8, sometimes with 6. And how do you take that call? I have to decode the instruction and try to understand how big the instruction is. It may take time. Here, I should not bother about what is going to be the instruction. I am only bothering about once the instruction is brought, before the instruction reaches the pipeline register, I have already updated my PC. So this is what happens in an instruction fetch stage. Now I am moving to the next stage. So whatever diagram we are seeing, I am showing stage by stage. First I showed only instruction fetch. Now you can see that there is an IFID register. The next pipeline register is IDEX register because it interfaces between ID stage and EX stage. So this is the first one we have seen. Now it is the IDEX stage. This stage is also known as instruction decode stage as well as register fetch stage. So it is known as ID. Now what is instruction decode? The process by which your microprocessor will understand what the operation is. See, when you fetch an instruction, it's a binary value that you are bringing, 1, 0, 0. Some ones and zeros are there. How do you know whether it's an add or a load or a jump instruction? You have to look at the bit pattern and the control unit. We will talk about the control unit design later. The control unit should have a mechanism to understand these bits and tell, okay, this is an add operation, or this is a jump operation, this is a comparison operation. So the process by which you understand what the operation is known as a decode instruction. Now, upon decoding, if you come to know that this is an instruction where some of the operands are in the registers, then I go to that register. So if you have, let's say this decode operation has 2 stages. Stage 1 is known as decoding the instruction and stage 2 is known as register reading. If at all any operands are in the register, then I go to those registers and bring the data. That's what you can see here. This stage is having access to the registers in the processor. So from where will you get the register number? Because we know from the instruction format, if it is an add R1, R2, R3, then R1 is the destination register. R2 and R3 are the source registers. So R2 and R3, contents of R2 and R3, I am reading from the register file. And then I bring them. The content of R2 and R3 will be stored in the IDEX register. At the same time, the opcode, it brings adding. So the bit pattern which represents that it is an add operation, that opcode is also I'm going to save. But I know that sometimes it can be an I-type instruction, like we have already discussed. The second category of instruction is I-type, where it has a 16-bit sign extension. So in that case, there are 2 registers. So along with the register value, I am going to have a sign extension also that is to be here. And sometimes if it is a read operation, then I have to tell whether it's a read operation or not. So some control signals also flow. Let us try to take an example. Consider add R1, R2, R3. Let us say this is going to be an instruction. And the 32-bit binary equivalent is, I'm going to write in hexadecimal. So A stands for 1010, 3 is 0011. Like that, this is the 32-bit combination of the value. Let us say this 32-bit is already available in the IFID register. Now, for the time being, let us imagine this A3 represent. This is not a MIPS encoding. I'm just trying to tell you how fixed length encoding works. Let us imagine this A3 is going to represent add. So this is A 1010 and 0011. So this represents A. So the control unit will look into the first 8 bits and trying to understand what is the operation. So when I come to know about this pattern, then and there itself I realize it is an add operation. This will tell you it is R1. This will tell you it is R2. And the third one will tell you it is R3. That's the way how we are going to look at it. This is an example. But in our MIPS case, it is not 8-bit divisions. It is 6-bit plus 5-bit plus 5-bit plus 5-bit. Like that we have already seen in the R-type instruction. Now what the beauty of this is, I know that whether it is an add or subtract, I'm not really bothered. I know that one of the source operand is R2. So the content of R2 anyway I have to bring. Another source operand is R3. So the content of R3 also I have to bring. So both the values I will be ready. In the meantime, decoding will happen. I'll come to know this is going to be my opcode. That means it is an add operation. So I will pass a signal known as add. Suppose if it is let's say going to be, this is going to be an I-type instruction where I'm mentioning an opcode portion, one register known as the destination register R1. There's a source register known as R2, and there is a 16-bit displacement value, or here it is known as immediate value. So 8 is represented as a 16-bit value. So in the register, upon decoding, I have to bring the content of R2. The content of R2 will come from register file to IDEX. The immediate value, so as such, the value 8 represented as a 16-bit value come through the sign extended portion. So what I need to do is in subsequent stages, this is a load instruction. Load means I will transfer contents from memory to processor. So in subsequent stages, I have to compute the effective address. The effective address is computed in the next stage, but in order to compute effective address, I require 2 things. First is known as the base register value, that is the value of R2. Second one is known as the displacement or an immediate value. So 8 and content of R2 has to be added in order to get the address. So the content of R2 will go and the sign extension value of 8 also will go. In the meantime, decoding will happen. So the R1 value, anyway, it should not. The meaning is ultimately the result has to be stored in R1. So R1 is a destination register. So I will tell the details of that into this. And then I go for telling what is the opcode all about, load. Here also, this represents load. This represents R1. And whereas this is going to represent your R2. And this is going to represent your 8. But in actual case, it is going to be 16-bit. I just tell this in order for you to understand it easily. Now coming to the third stage, which is known as execution stage. For an ALU instruction means an instruction with 3 operands. All of them are registers like add R1, R2, R3, sub. And there is no multiplication instruction directly here. I will tell you later why. So any instruction with 3 register operands, we call it as an ALU instruction. So for ALU instruction, your third stage will perform the operation because your operands are already available in IDEX register. One will come through this channel and enter one input of ALU. The second operand will come through the second channel and reach the second input of ALU. And you give the corresponding operation signal to ALU, and the ALU produces the result. The result will be stored in EXMEM register. But if it is a load or a store instruction, you are not executing it. This is the time where I compute the effective address. So for ALU instruction, your third stage is known as execution stage. For load store instruction, the third stage is known as effective address cycle stage. So for memory references, you calculate the effective address. So like what we discussed previously, load word R1, 8 of R2, content of R2, as well as the 16-bit sign extended 8 is also available in IDEX register. You add them together. Content of R2 is added with 8, and whatever you are getting, that is known as effective address. If it is a register ALU instruction like add R1, R2, R2, then here also what we do, we will add the content of R2. Content of R2 is added 2 times. One operand is R2, second operand is also R2. Then you perform the add operation and then get the result. Now we come to the fourth stage, which is known as the MEM stage. In the MEM stage, this is used only for two instructions, a load instruction and a store instruction. All others, if it is like an ALU instruction, the contents of EXMEM register will get simply copied to the mem write back register. Means essentially there is a one cycle delay. That's all. This is designed in order to make sure that every instruction is going to get complete over 5 cycles, and for some instruction this memory is not required. So this is used only for load and store instruction. Load the memory and store in register. That is called load word. Load word R1, 8 of R2. Meaning is R2 plus 8 is the effective address. Let us say that corresponds to 2000. Go to 2000. Transfer the content of 2000. That's a 4-byte value. The 32-bit value is loaded to R1. Similarly, store means just reverse. 16 of R4. That means content of R4 plus 16. That will give you the effective address. Contents already present in R3 should be returned to that effective address. It is these two. Accessing memory. The address is already available in EXMEM register. In the case of a store operation, the content of R3 as well as the effective address, both are available in EXMEM register. For the case of a load instruction, effective address, that is 8 plus content of R2, that is available in EXMEM register. So in the MEM stage, whatever is the address, if it is a load, you go to the location and bring its contents. So the contents from 8 plus R2 will reach the mem write back register. For a store operation, your operation is getting over. Whatever is available, the content of R3, which is present in EXMEM register, each will be returned to the memory. That's the way how this works. And then you go to the last stage, which is known as the write back stage. So this write back stage is used only by those instructions whose result is to be returned to a register. Let's say load word, the result has to be stored in R1. In this case, add, the result has to be stored in R1. So any writing into the register file, it will be taken by the write back register. So the register file is read in the ID stage. You are going to write into the register file in the write back stage. So these are the 5 stages that you can see. Now, if you look at all the 5, you will be able to understand instruction fetch, instruction decode, execute, memory access, and then the write back. Now, the peculiarity is each of them are carried out by independent units. So each may have its own latency, and your processor clock is given to these pipeline latches. So all the latch will be triggered together, which is known as the beginning of a clock cycle. In the beginning of a clock cycle, what happens? The instruction decode unit will take whatever is available in the IFID pipeline register, perform the decoding and reading the register, and then at the end of the clock cycle, it will write into the IDEX pipeline register. And what will be done by the EX unit? Whatever is present in IDEX register, depending on operation, either you add it or you compute the effective address and write the result. MEM stage, depending on what is there. If it is an add operation, you simply take the value from EXMEM and store into MEM write back. If it is a load store operation, go to memory and perform the operation. And what the write back will do every cycle, whatever is written in MEM write back pipeline register, its contents are to be copied and returned to the register file that is already been mentioned. So all the 5 units are busy essentially. So each instruction can take at most 5 clock cycles. Instruction fetch, what it will does, based on program counter value, it fetch the instruction from memory and update PC. Instruction decode or register fetch, which is abbreviated as ID, will decode the instruction and read the contents of a register because it uses a fixed field decoding. And you can even perform whether 2 registers are same or not. And for branch instruction, it will check whether the branch has happened or not. That also happened in the ID stage. And execution stage, what we discussed, for register operation, it will calculate, it will perform the operation. For memory, it will calculate the effective address. MEM stage, for load and store instruction, load means it read from the memory using the effective address. Effective address. And the last stage is known as a write back. So whatever is the result of an operation, whether it's a load operation or for a register operation, whatever is the result that is obtained, it has to be written back to the register. These are the 5 stages. So in short, we have IF, ID, EX, MEM, and write back. So branch instruction will get over in 4th clock cycle. Store will get over in the 4th clock cycle, because the last clock cycle we can tell that. So write back, essentially they are not doing any operation. All other instruction, because the result is being reflected in a register, it will make use of the write back operation. So this is the way how things are being carried out. So if you look at a program which consists of 5 instructions, I plus 1, I plus 2, I plus 3, and I plus 4. In clock cycle number 1, I perform instruction fetch of I. In clock cycle 2, I move to the decode stage. Like that, at the end of the clock cycle 5, I complete ith instruction. But in the meantime, already I plus 1, I plus 2, and I plus 3 have entered the instruction pipeline. So if you look at clock cycle number 5, the write back stage of an instruction pipeline is busy writing the result of the ith instruction. The mem stage is performing memory access for the I plus 1th instruction. The EX stage is performing EX operation. Either it can be an address computation or it can be an ALU operation for I plus 2 instruction. The ID stage is performing instruction decode for I plus 3 instruction. And I plus 4th instruction is fetched by the IF stage. So all the 5 units are busy, but they are busy with 5 different instructions. Look at, you can see after clock cycle 5, in every clock cycle, let's say 6, 7, 8, new instructions are getting completed. So every cycle I can start a new instruction. Now look at the throughput. In the normally an unpipelined design, I can start your next fetching only at clock cycle number 6. But here I am not waiting for the first instruction to get over. I am slowly starting the execution operation of the second instruction before completion of the first one. At any given point of time, there are 5 instructions already in a partially execution state. This technique by which you partially overlap the execution of instructions is known as instruction pipelining. And if you look into, if you try to visualize it, first I read instruction from instruction memory, then I read from registers, then I perform operation in ALU, then I go to data memory, then I'm again going to write. So this will tell you what are the hardware resources which are being utilized in these various clock cycles. So fetching done in instruction memory, decoding and reading operations. Reading from register happen from register file. Similarly, writing also happen in register file. ALU perform effective address computation for load store. It will perform the operation as far as an ALU operation is concerned, and data memory performs this operation. So this is how you visualize. This is the ideal case, but it will not happen always. But let me know if there is any query in the topics that is covered till now. So is there any query? Please raise your hands if you have any query in the topic that is already covered. Yes, Anirudh, please unmute and ask your query.
Sir, if we look at the clock cycle 5,
yeah,
we are using registers in 2 places.
Hmm.
Say if I want to write to the same register and I'm using also the same register, will there be any problem?
So we have separate ports. One is called a read port, other one is known as a write port. So clock cycle 5 will perform write operation on register, whereas clock cycle 2 operation will perform a reading from register. So the registers are multi-ported. So I can solve the issue.
Okay, sir. Thank you.
So there are 2 more slides which will tell. So now let us see what are the issues with the pipeline. The ideal case, we assume that uniform subcomputation. That means we assume the whole basis of pipeline is the computation to be performed can be evenly partitioned into uniform latency subcomputation. Means IF, ID, EX, MEM, and write back all will take same amount of time. The reality, it is not. Not all pipeline stages may have uniform latency. So what is the impact of ISA? While designing the instruction set architecture, like the instruction encoding that you learned in first half of the course, make sure all instructions are of uniform complexity. That is why you will get advantage from the RISC instruction. Memory access is a critical subcomputation. Memory access may take more time. So IF and MEM stage may take more time. So we have to reduce memory addressing modes as much as possible. So using faster cache memories can be one way in which you can reduce. So in order to get performance, all stages has to be uniform. The two stages which are creating bottleneck, they are IF and MEM stages. The second case is you feel identical computation. We feel that the same computation, all these 5 computations has to be performed repeatedly on large number of input data set. We feel every operation has to go through all these 5 stages. The reality is some pipeline stages may not be used, like we are not using MEM stage at all. We are not using write back stages for store operation and for branch operation. We are not using MEM stage for ALU instructions. So every instruction you cannot represent that, it should go through all the 5. But what we do, the impact of ISA is you reduce the complexity and diversity of instruction type such that you can fit all of them into this. So here, even though I'm not using a stage in between, that will come as a one cycle unwanted delay. So for ALU instruction, for third clock cycle, I perform the execution operation. I get the result, but I will write the result only in the 5th clock cycle. In 4th clock cycle, I am sitting idle. So this idleness will happen because I wanted to reduce the complexity and make it uniform for all. If everyone has to take uniform 5 clock cycle, then I have to bear this penalty. So basically your RISC architecture is motivated by this one. And the third one is we assume all instructions are mutually independent. The reality is pipeline cannot proceed the way how we saw today. Sometimes a later computation may require the result of a previous computation. Let's say my third instruction wanted to operate on a data which is produced by the first instruction. So before the first instruction complete, how can I read the data of the third instruction? So the impact is we may have to find out dependency checking. And so what I want to try to say is there are problems. We will try to address these problems and how an effective pipeline is being implemented. So you have to reduce your memory addressing modes as much as possible, because in memory addressing modes, dependency detection is very difficult. And wherever possible, there should be a mechanism by which I know that, okay, this result is produced by someone else just before me, and I have to wait until he completes execution. So I have to delay myself. So when I delay myself, what will happen to subsequent instruction? These things we will learn in the next class. So whatever topics I'm covering, this is taken from Appendix C of the textbook, 5th edition. And so section C1 is what I have covered. And for those who missed and those who wanted to have a relook at it, you can refer to this YouTube link of the NPTEL video, and that will give you a clear concept about it. Okay. So that's all about for today. But then please tell, I can see only